The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Now, let's move on and briefly talk about the acid anhydrides, because they're the only ones that we haven't really discussed at length. Now, acetates are better electron withdrawing groups than either that we have in esters or amino group or the amide group that we have in amides. So what I mean by an acetate, I'm talking about that carboxyl group right there, okay? They're better at withdrawing electrons than the group we have in esters, which is that alkoxide group, or the group we have in amides, which is that amino group, okay? So that carboxyl group right there will withdraw electron density away from our reaction center right here, which is what makes acid anhydrides more reactive than either esters or amides. So resonance stabilization in an anhydride is comparable to that which occurs in esters, but the stabilization is shared between two carbonyl atoms. So each carbonyl group receives less stabilization than the ester carbonyl. I'm going to repeat that one more time. Each carbonyl group will receive less stabilization than the ester carbonyl. So we're talking about the effect of resonance. And remember, resonance will decrease reactivity. In the case of an ester, what we have is a compound that looks something like that. Okay? Now, that delocalization occurs across the system right here. But in the case of an anhydride, we have delocalization still occurring, but the only difference is that it's happening across two carbonyl groups. So right there and there. So the effect of resonance in acid anhydrides is not as pronounced as it is in esters, and that is why acid anhydrides will be more reactive than esters of comparable molecular weight. So let's recap. Acid anhydrides are better at induction than both amides and esters. And why is that? As you can see, this carboxyl group is better at inductively withdrawing electrons away from our reaction center right there. On the flip side, as far as resonance is concerned, resonance stabilization does occur in anhydrides, but not to the degree it occurs in both esters and amides. So now, as you can see, putting all this information together, we're getting a rationale for the order of reactivity that we observe. So I'm just going to draw out these compounds one more time at the bottom of the screen. So we have an acyl halide, and then moving from there, we go to our anhydride, and then moving from there, we move to our ester, and then moving from there, we go to our amide. So you have the most induction in an acyl halide and the least resonance effect also in an acyl halide, which is why they're most reactive, because remember, induction will increase reactivity, resonance will decrease reactivity, okay? So in the case of an anhydride, you do have some resonance stabilization, but not as much as you do as is the case in esters or amides. And you also have some degree of inductive electron withdrawal because of that carboxyl group, as you can see right there. That is why anhydrides are second on that list. Now, as far as esters are concerned, you do have resonance stabilization, but again, not to the degree that which you have in amides. And you also have some inductive electron withdrawal, as you can see in our generic ester right here, inductive electron withdrawal towards that oxygen atom, which makes the esters more reactive than the amides. Now, as far as the amides are concerned, you're talking about complete resonance stabilization. I mean, the bond between the carbon and the nitrogen is almost pretty much a double bond. And for that reason, the order of reactivity moves that way. And as you can see, that will be decreasing reactivity. And if you think about it in electronic terms, the inductive and resonance effects explain all of this. So I hope that makes sense, right? A little confusing. If you don't completely fully understand what we talked about, again, just review, but take home those two main concepts as far as induction and resonance is concerned.